Look up at the night sky, and what do you see? A blanket of stars, distant galaxies, perhaps the occasional shooting star. But what about the spaces in between? The voids where light seems to vanish, swallowed whole by something unseen. Those shadowy patches aren't empty. They're cosmic enigmacies known as dark nebulae, colossal clouds of dust and gas so dense they blot out the light behind them. These aren't just absences, they're active, dynamic regions where stars are born and secrets of the universe are hidden in plain sight. Imagine standing at the edge of one, staring into a darkness so profound it feels alive, shifting, whispering clues about the forces that shape our cosmos. What makes these dark nebulae so fascinating isn't just their ability to conceal, it's what they reveal when we look closer. Behind their inky veils lie puzzles that defy our current understanding. Some of these clouds shouldn't exist according to the laws of physics as we know them. Others harbor bizarre structures, tendrils of matter stretching across light years, or magnetic fields so intense they warp space itself. And then there are the whispers of something even stranger, the possibility that these nebulae might be hiding more than just stars. Could they be cosmic fingerprints of phenomena we've yet to name? Today, we're venturing into the heart of these mysteries, exploring 25 of the most perplexing dark nebulae ever discovered. Each one challenges our assumptions, from the way they form to the way they interact with the universe around them. Some will make you question everything you thought you knew about space. Others might leave you with more questions than answers, and that's the beauty of it. Because the universe isn't here to give us easy explanations. It's here to keep us curious, to keep us searching. So let's begin this journey into the shadows where the most intriguing secrets of the cosmos are waiting to be uncovered. Barnard 68 is one of the most unsettling sights in the night sky, not because of what it shows, but because of what it hides. Nestled in the constellation Ophiuchus, this dark nebula is so dense that not a single star's light pierces through it. Stare into its abyss and you're met with pure, unbroken blackness, as if someone cut a hole straight through the cosmos. Astronomers have nicknamed it the black hole of the sky, not because it's an actual black hole, but because its light-devouring presence creates the same chilling effect. What makes Barnard 68 so fascinating isn't just its darkness, it's what's happening inside. This isn't some lifeless void. It's a molecular cloud, a swirling mass of dust and gas so cold that molecules actually form within it, clumping together in the frigid emptiness. And here's where things get even more interesting. Right now, Barnard 68 isn't just sitting there, it's collapsing. Slowly, over millions of years, gravity is pulling its material inward, compressing it into tighter knots. That's how stars are born, and while Barnard 68 hasn't yet sparked any new suns, it might just be a cosmic nursery in waiting. Scientists have detected strange ripples in its structure, subtle hints that pockets inside could be on the verge of igniting. Picture that a place where light itself is snuffed out could one day blaze with newborn stars. It's a paradox that captures the duality of dark nebulae. They're both cosmic destroyers of light and cradles of creation. But here's the real question keeping astronomers up at night. Why is Barnard 68 so perfectly dark? Most dark nebulae have at least a few faint stars peeking through. Not this one. Some researchers think its dust particles might be unusually fine, scattering light in ways we don't fully understand. Others speculate that its shape, a near-perfect spherical blob, plays a role. Whatever the reason, Barnard 68 remains one of the starkest reminders that even in the brightest corners of the universe, darkness has its own story to tell. The Coalsack Nebula stares back at you from the heart of the Milky Way like a cosmic ink blot so dark, so prominent that ancient cultures saw it as something far more than just an absence of light. To the naked eye in the southern hemisphere, it's an unmistakable stain against the starry river of our galaxy, a patch of night that seems to swallow constellations whole. But this isn't just a void. It's a laboratory of creation where the raw ingredients of stars mingle in the cold embrace of space. Long before telescopes revealed its secrets, Aboriginal astronomers wove the Coalsack into their celestial stories. Some saw it as the head of an emu stretching across the sky, its dark form tracing the outline of a sacred creature. Others interpreted it as a portal to the dreamtime, a bridge between worlds. These weren't just myths, they were sophisticated maps of the cosmos, proof that humanity has always been captivated by this enigmatic shadow. Modern astronomy has peeled back layers of the Coalsack's mystery, revealing a turbulent sea of dust and gas spanning 30 light-years. What makes it extraordinary isn't just its size, but its composition. The nebula's grains are unlike typical interstellar dust, finer, sharper, almost glass-like, scattering light in ways that still puzzle scientists. Some theories suggest violent supernova long ago shattered these particles into their unusual forms, leaving behind a cosmic fingerprint of ancient stellar explosions. Yet the real magic lies in what's brewing beneath that darkness. Infrared telescopes have pierced the Coalsack's veil, uncovering pockets of gas contracting under their own gravity, stellar embryos taking shape in the cold. One particular region, nicknamed the Knot, glows faintly with the heat of newborn stars, their light struggling to escape the dusty womb surrounding them. It's a slow-motion birth playing out over millennia, hidden from visible light but teeming with invisible activity. But here's the twist, the Coalsack shouldn't be this dark. Given its distance and the usual density of such clouds, at least some starlight should filter through. Instead, it remains eerily opaque, as if the laws of physics themselves bend within its boundaries. Some researchers speculate that magnetic fields crisscrossing the nebula trap dust in dense sheets, while others propose unseen molecular bonds between particles are amplifying its light-blocking power. Whatever the cause, the Coalsack stands as a reminder that even the most familiar cosmic landmarks can harbor profound surprises. The Snake Nebula slithers through the constellation Ophiuchus like a shadowy serpent frozen mid-strike, a cosmic predator woven from dust and darkness. This filamentary wonder stretches nearly 30 light-years across the sky, its twisting tendrils so distinct that they appear almost sculpted by an unseen hand. But this isn't the work of artistry, it's the brutal elegance of gravity, warping and compressing the nebula's structure into those eerie, serpentine curves. What makes the Snake Nebula truly mesmerizing isn't just its shape, but the forces that shaped it. Unlike the dense, clumpy darkness of Barnard 68, this nebula is a delicate tapestry of threads, each one a magnetic highway guiding particles through space. Astronomers believe powerful shock waves from nearby star formations may have initially stretched the cloud into its elongated form, like taffy pulled between invisible fingers. Then gravity took over, amplifying every kink and bend until the nebula became the cosmic ribbon we see today. For astrophotographers, the snake is a bucket list target, and not just for its dramatic silhouette. Its edges glow faintly where starlight bleeds through thinner patches of dust, creating an ethereal halo effect that's irresistible to cameras. Long exposure shots reveal something even more startling: hundreds of background stars twinkling through the nebula's gaps, as if the serpent's body is studded with tiny, piercing eyes. It's a reminder that darkness isn't absolute. Even the most opaque cosmic structures are riddled with holes, windows to the universe beyond. But the real mystery lies in the snake's spine. Radio telescopes have detected bizarre, knot-like clumps along its length, regions where the dust is so tightly wound, it defies typical models of cloud collapse. Some scientists speculate these could be the earliest stages of star formation, while others argue the magnetic fields here are simply too chaotic for stars to ever ignite. One thing's certain, this celestial serpent still has secrets coiled within its shadows, waiting to strike curiosity into anyone brave enough to look closer. The Pipe Nebula cuts a stark silhouette against the starry backdrop of the Milky Way, its bowl and stem so perfectly defined it looks like some celestial giant left their smoking pipe floating in space. Found near the galactic center in Ophiuchus, this sprawling dark nebula stretches over 7 degrees across the sky, roughly 14 times the width of a full moon. But what appears as a simple shape to our eyes is actually a labyrinth of dust lanes, so dense they blot out the light of 500,000 stars behind them. Peer closely at the pipe's stem through a telescope and you'll notice something startling. The darkness isn't uniform. Fissures and tendrils branch through its structure like cracks in obsidian, revealing patches where distant starlight barely seeps through. These variations aren't random. They're cosmic breadcrumbs leading scientists to one of the nebula's greatest secrets, the three-dimensional architecture of interstellar dust. By measuring how sharply the pipe's edges block starlight at different wavelengths, astronomers have mapped its density in unprecedented detail, discovering that what looks like a flat shadow is actually a layered veil stretching hundreds of light years deep. Here's where it gets even more intriguing. The pipe isn't just obscuring light, it's sculpting it. Stars shining through its thinner edges appear redder, their blue wavelengths scattered by dust grains in a process eerily similar to Earth's sunsets. This phenomenon, called interstellar reddening, turns the nebula into a colossal filter, revealing the size and composition of its particles. Some grains are likely coated in frozen carbon monoxide, giving them a frosty outer shell that amplifies their light-blocking power. Others may contain microscopic diamonds, remnants of ancient stellar explosions that seeded the cloud with stardust. Yet the pipe's most captivating feature might be what it's hiding. Nestled within its bowl lies Barnard 59, a dense knot of gas so thick it's essentially a dark nebula within a dark nebula. Infrared observations suggest this region is on the brink of collapse, its molecules huddling together against the cold as gravity prepares to work its magic. In a few million years, the pipe's stem might not just be a shadow. It could become a bridge to newborn stars, their light piercing through the very dust that once kept them invisible. For now, though, it remains a silent sentinel near the heart of our galaxy, reminding us that even the simplest cosmic shapes can hold galaxies' worth of secrets. Tucked away in Orion's sword, far from the glare of the constellation's famous stars, lies Lynn's dark nebula 1622, a ghostly smudge of cosmic dust so faint most star charts don't even mark it. While Orion's nebulas like M42 bask in the spotlight, this unassuming shadow quietly harbors some of the coldest temperatures ever recorded in space, a frigid -260 degrees Celsius. That's just 13 degrees above absolute zero, the theoretical point where all molecular motion stops. At these extremes, ordinary gases freeze solid, and the nebula's dust grains become icy time capsules, preserving molecules unchanged for millions of years. What makes LDN 1622 so captivating isn't just its chill, it's the way it defies expectations. Most dark nebulas of this size are static, but observations reveal subtle ripples in its structure, as if some unseen force is stirring its depths. Radio telescopes have detected faint whispers of carbon monoxide molecules spinning violently within the cloud, hinting at turbulent motions beneath that inky surface. Some astronomers speculate these could be traces of past supernova shocks, rippling through the nebula like echoes of a cosmic explosion. Others propose a more tantalizing idea, that LDN 1622 might be feeling the gravitational pull of something massive hidden just beyond our view. Here's where the puzzle deepens. This nebula sits suspiciously close to Orion's star-forming factories, including the Sigma Orionis cluster. While it's too cold to birth stars itself, there's growing evidence it could be a reservoir of raw material, a cosmic warehouse feeding younger, hotter nebulas nearby. Submillimeter telescopes have spotted tendrils of dust stretching toward neighboring regions, suggesting LDN 1622 might slowly be dissolving, its particles siphoned away to build new suns elsewhere. Yet the most enduring mystery is one of perspective. From Earth, LDN 1622 appears isolated, a lonely blot against Orion's brilliance, but three-dimensional mapping suggests it might actually be the foreground curtain of a far larger structure, part of Orion's sprawling molecular cloud complex. If true, this faint nebula could be a key to understanding how dark matter shapes the galaxy's star-forming skeleton, one silent, freezing thread in a tapestry we're only beginning to unravel. Amid the glittering backdrop of Cygnus, the ink spot nebula stands out like a flaw in the cosmos, a patch of darkness so pure and small you could blot it out with your thumb at arm's length. While most dark nebulae fade gradually into their surroundings, this one cuts a razor-sharp boundary against the Milky Way's starry canvas, as if someone dipped a brush in cosmic ink and pressed it onto the sky. At just half a light-year across, it's tiny by nebula standards, yet its opacity is unmatched, blocking 100% of the starlight behind it with almost surgical precision. Scientists first assumed the ink spot's dramatic contrast came from sheer density, a simple matter of packing enough dust into a small space, but when radio telescopes measured its mass, they got a shock. This nebula weighs no more than your average interstellar cloud. So how does something so lightweight cast such an inky shadow? The answer might lie in the structure of its dust grains. Unlike the fluffy, fractal-like particles found in most nebulae, the ink spot's dust appears unnaturally smooth and uniform, like finely ground graphite scattered in perfectly aligned layers. This unique arrangement could explain why light struggles so hard to penetrate. Photons aren't just hitting dust. They're navigating a labyrinth of ultra-flat surfaces that scatter them sideways instead of forward. Then there's the nebula's eerie two-dimensional quality. Most cosmic clouds reveal depth when studied closely, their mottled textures betraying complex three-dimensional shapes. The ink spot defies this entirely. Whether viewed from Earth or through the Hubble Space Telescope, it maintains the same stark flatness, like a cardboard cutout pasted onto the starfield. Some researchers propose its dust might be trapped in an immense, nearly edge-on disk, a structure that would make it the cosmic equivalent of holding a sheet of paper sideways. Others suggest it could be a rare example of a thin shell nebula, the remnant of a stellar explosion that sent debris flying outward in an expanding sphere so perfectly symmetrical that from our vantage point it appears paper-thin. Yet the most tantalizing clue comes from what surrounds the ink spot. Infrared surveys show it drifting through a region littered with the shattered remains of ancient supernova. Could this nebula be a gathering of stardust forged in those violent deaths? Its dust grains do show unusual traces of heavy elements like silicon and iron materials typically forged in stellar explosions. If so, the ink spot might be less of a cloud and more of a cosmic scrapbook, its darkness preserving atomic fingerprints from stars that died before our solar system even formed. For now, this tiny shadow remains one of the sky's most deceptive enigmas. Its modest size belies the complexity within, proving once again that in the cosmos, darkness isn't merely the absence of light, it's a language, one we're only beginning to decode. The dark Doodad Nebula slinks through the constellation Musca like a cosmic caterpillar mid-crawl, a whimsically named shadow stretching over 30 light-years of southern sky. What it lacks in conventional astronomical grandeur, it makes up for in sheer scientific intrigue, serving as one of the best laboratories in the galaxy for studying an invisible force shaping the universe, magnetic fields. Unlike the chaotic sprawl of most dark nebulae, the Doodad's dust grains are eerily disciplined, lining up like iron filings around a magnet. This alignment isn't random, it's a cosmic fingerprint of the magnetic field threading through the cloud, a force strong enough to choreograph the orientation of countless microscopic particles across light-years of space. Here's how astronomers spotted the Doodad's hidden magnetism. When starlight passes through the nebula, something extraordinary happens. The light becomes polarized, its waves vibrating predominantly in one direction. This subtle shift, detectable only with specialized filters, reveals how the nebula's dust grains are all pointing the same way, like countless tiny compass needles. By mapping these polarization patterns, scientists have reconstructed the Doodad's magnetic field in 3 dimensions, unveiling a sprawling network of invisible lines that twist and arc through the cloud. These forces aren't just decorative, they're actively stifling star formation, preventing the gas from collapsing under its own gravity by propping it up with magnetic pressure. Yet the Doodad's quirks don't end there. Its dust grains are interstellar oddballs coated in icy mantles of frozen water and carbon monoxide that amplify their light-scattering properties. In some regions, these icy coatings have grown so thick they've begun forming microscopic tunnels and ridges, turning each grain into a complex frosty sculpture. Infrared telescopes have even detected organic molecules clinging to these surfaces, the same kinds of carbon-based compounds that, in other parts of the universe, might eventually seed life. It's a reminder that darkness isn't sterile. Even here, in the coldest voids, chemistry is at work. What truly sets this nebula apart, though, is its delicate transparency. Unlike the inky blackness of Barnard 68, the Doodad lets just enough starlight through to create an ethereal backlit effect, its silhouette fringed with a faint bluish glow. This isn't just pretty, it's a clue. The blue tint comes from shorter wavelengths scattering off the nebula's tiniest dust particles, a phenomenon similar to why Earth's sky appears blue. By measuring this scattering, astronomers have calculated the exact size distribution of the Doodad's grains, down to fractions of a micrometer. Few other dark nebulae offer such a clear window into the universe's hidden scaffolding. So why does this quirky named shadow matter? Because it challenges the assumption that dark nebulae are merely passive obstacles. The Doodad proves they're dynamic participants in the cosmos, their dust acting as both tracers of invisible forces and architects of stellar birth, or in this case, stellar delay. Every alignment of its grains, every ripple in its magnetic field, is a silent dialogue between dust and the universe's unseen scaffolding. And as telescopes grow more advanced, this unassuming cosmic caterpillar may yet reveal how magnetism weaves the tapestry of galaxies themselves. The Horsehead Nebula's famous silhouette, that iconic cosmic profile, wouldn't exist without the shadowy giant lurking behind it. Most photographs capture the Horsehead as a standalone marvel, but peel back the layers and you'll discover Barnard 33 is just the tip of the iceberg. The real architect of this celestial masterpiece is LDN 1630, a vast molecular cloud so dense it acts like a cosmic backstop, absorbing the furious radiation from nearby stars and casting the Horsehead's shadow in stark relief. Without this dark counterpart, the Horsehead would simply dissolve into the glow of its surroundings, its shape erased by the very forces that make it visible. What makes this pairing so fascinating is the delicate balance between destruction and persistence. The Horsehead isn't a static sculpture, it's a battlefield. Sigma Orionis, a blazing young star just 15 light-years away, bombards the nebula with ultraviolet radiation, slowly evaporating its gas and dust. This process, called photoevaporation, should have shredded the Horsehead to nothing by now, yet it endures thanks to LDN 1630's protective bulk. Think of it like a mountain shielding a valley from a hurricane. The dark cloud absorbs the brunt of the stellar onslaught, leaving the Horsehead's distinctive shape to weather the storm at a slower pace. Scientists have measured this evaporation in action. Telescopes tuned to specific molecular emissions reveal tendrils of gas streaming away from the Horsehead's edges, their trajectories warped by magnetic fields threading through LDN 1630. These observations show something remarkable. The shadow isn't just blocking light, it's sculpting the nebula's very survival. By analyzing how quickly material erodes from the Horsehead's main versus its more shielded base, astronomers can clock the evaporation rate with precision, watching as the nebula loses roughly 1 Earth mass every 1,500 years. But here's the twist: LDN 1630 isn't just a shield, it's a time capsule. While the Horsehead faces destruction, the dark cloud behind it remains eerily unchanged, its colder, denser interior resisting the radiation that's peeling away its neighbor. Infrared surveys reveal pockets within this shadow where temperatures hover near absolute zero, preserving molecules in a near-perfect deep freeze. Some of these compounds, like diazonilium and deuterated ammonia, are essentially cosmic fossils untouched since the cloud's formation. The Horsehead and its shadowy counterpart offer a rare glimpse into two extremes, one structure fighting for survival in the galactic spotlight, the other lurking in the wings, patiently hoarding the raw materials of future stars. It's a partnership as old as the universe itself: light and dark, erosion and preservation, playing out on a scale so vast it takes light centuries to cross the stage. And in their dance, we see the hidden forces that shape not just nebulae but galaxies. The Great Rift slashes through the Milky Way like a scar across the galaxy's luminous face, a jagged divide so vast it was noticed by civilizations long before telescopes existed. From the northern hemisphere, this dark river seems to split the starry band of our galaxy in two, stretching from Cygnus in the north all the way down to Sagittarius near the galactic center. But what ancient stargazers saw as a celestial crack is actually a cascading front of dark nebulae, layer upon layer of dust clouds stacked along our line of sight, each one adding to the illusion of a single yawning void. Together, they form one of the most imposing structures in our sky, not just a barrier to light, but a filter reshaping our very view of the universe. Early cultures wove the Great Rift into their cosmologies with striking creativity. The Inca saw it as a celestial serpent, its Inkai coils holding the Milky Way in place. Polynesian navigators used its contours as a nautical map, reading the darkness like sailors charting gaps between islands. In West Africa, the Bambara people interpreted it as the blackened scales of the cosmic fish that birthed all matter. These weren't mere myths, they were sophisticated attempts to explain an anomaly visible to the naked eye, a darkness so profound it demanded stories. Modern astronomy has revealed the rift's true nature, a sprawling complex of at least 18 major dark nebulae, including familiar names like the Coalsack and the Pipe, all drifting between us and the galaxy's heart. Their combined effect blocks roughly 20% of visible light from the Milky Way center, a cosmic curtain so thick it once left astronomers guessing what lay beyond. That changed when infrared telescopes like Spitzer and Webb turned their gaze toward the rift. Where optical light fails, longer wavelengths slip through dust like ghosts through walls, unveiling star clusters and nebulae previously hidden. Some of these discoveries rewrite galactic history. Behind the rift's darkest segment, astronomers found a star desert, a region spanning 3,000 light-years with suspiciously few young stars. The leading theory suggests the rift's dust may have literally starved this zone of star-forming material, creating a celestial dead zone in what should be a bustling galactic neighborhood. Other infrared surveys reveal the opposite phenomenon, pockets where the rift's dust is collapsing into new stellar nurseries, proving that even these light-devouring clouds are part of the galaxy's life cycle. Yet the rift's greatest gift to science might be its role as a natural laboratory. By studying how different wavelengths interact with its dust, researchers have decoded the precise size distribution of interstellar grains, some as fine as cigarette smoke, others as coarse as sand. Certain sections exhibit bizarre properties, like the Taurus dark cloud complex, where dust particles align with magnetic fields to polarize starlight in mesmerizing patterns. Other areas show chemical oddities, with ice-coated grains harboring complex organic molecules normally seen in comet cores. What emerges is a portrait of the Great Rift not as an obstacle, but as a lens, one that distorts our view while revealing secrets invisible in pure light. It reminds us that darkness in space is never empty. It's an active participant in the cosmos, shaping what we see, what we miss, and ultimately what we understand. While the southern Coalsack dominates Milky Way lore with its Inkai sprawl, its lesser-known northern cousin quietly drifts through Cygnus, a shadowy echo with its own cryptic tale. The northern Coalsack lacks the southern version's monolithic presence, appearing instead as a shattered mosaic of dark patches scattered along the galactic plane. Through binoculars, it looks less like a single cloud and more like spilled ink diffusing through cosmic parchment, its edges frayed into tendrils that dissolve among the stars. This fractured appearance has fueled a century-long debate. Are we seeing one nebula stretched thin by interstellar winds, or a celestial illusion, multiple unrelated clouds lined up by chance? Here's where modern astronomy weighs in. Radio telescopes mapping molecular gas reveal something startling. These fragments share nearly identical velocities, moving in lockstep through space like a school of fish. That synchronization suggests a common origin, perhaps the remnants of a single massive cloud ripped apart by shockwaves from ancient supernova. Yet there's a twist. Spectroscopic analysis shows subtle chemical differences between segments, with some regions richer in complex carbon chains while others harbor unexpected concentrations of frozen nitrogen. These variances could imply the northern Coalsack isn't just one disrupted nebula, but a family of smaller clouds that formed close together, their compositions altered by local stellar radiation over millennia. The northern counterpart also behaves differently than its southern relative when confronted with starlight. Where the southern Coalsack absorbs nearly all visible light, its Cygnus sibling lets faint glimmers through, particularly in the red part of the spectrum. This isn't just a density quirk, it's a clue about dust grain size. Larger particles tend to scatter blue light, think Earth sky, while smaller ones let red wavelengths pass almost unscathed. The northern Coalsack's ruddy glow hints at an abundance of unusually tiny grains, possibly shattered by ultraviolet radiation from Cygnus's young, hot stars. Then there's the matter of missing mass. For a nebula covering so much sky, the northern Coalsack weighs shockingly little, about 500 times the Sun's mass spread over an area larger than 30 full moons. Most dark nebulae this expansive would be 50 times heavier. Some researchers propose we're witnessing the final act of a dissolving cloud, its material evaporating into the interstellar medium. Others argue its wispy nature could be intrinsic, a relic from an era when the galaxy's dust was more diffusely distributed. What makes this nebula truly special, though, is its role as a cosmic prism. Starlight passing through its thinner edges becomes polarized, its waves aligned by magnetic fields threading the dust. By measuring this effect, astronomers have mapped otherwise invisible forces shaping our galaxy. The northern Coalsack's magnetic imprint suggests turbulence fields twisted like tangled yarn, possibly by the same stellar winds that fractured the cloud itself. Whether solitary wanderer or scattered siblings, these northern shadows challenge our assumptions about how dark nebulae evolve. They prove opacity isn't just about density, it's a dance between dust, light, and the forces that stretch a nebula's story across the sky. The Cygnus X complex doesn't just hide in the constellation Cygnus, it dominates it, a sprawling metropolis of gas and dust where stars are born in chaos and scale beyond imagination. This isn't just another dark nebula, it's a cosmic factory floor where dark lanes twist like conveyor belts feeding material into the birth of stellar giants. Covering over 600 light-years, Cygnus X is one of the most massive star-forming regions in our galaxy, a place where darkness and light wage a constant tug of war, each sculpting the other into breathtaking shapes. At first glance, Cygnus X appears as a fragmented tapestry, patches of inky blackness threaded between glowing nebulae like the North America and Pelican. But radio and infrared observations reveal the truth. These dark veins are the backbone of the entire complex. They funnel cold molecular hydrogen into dense knots where gravity takes over, crushing the gas until nuclear fusion ignites. The result, stars unlike anything in our neighborhood. While most stellar nurseries produce modest suns, Cygnus X specializes in monsters, O-type stars, behemoths dozens of times the mass of our Sun, blazing so fiercely they can ionize entire nebulas with their ultraviolet fury. What sets Cygnus X apart is the sheer violence of its creation process. Turbulence here isn't just a side effect, it's the engine. ALMA telescope images show dark filaments colliding at supersonic speeds, triggering cascades of star formation like dominoes falling in every direction. Some of these collisions create hub filament system structures where dark lanes converge like spokes on a wheel, channeling gas towards central hubs where massive stars erupt to life. One such hub, dubbed Dia-21, hosts a stellar nursery so violent it's launching jets of material at 500,000 miles per hour, punching through surrounding dust like cosmic artillery. Yet the most intriguing puzzle lies in the dark nebula's role as a cosmic regulator. While the region's bright nebulae get all the attention, it's the shadowy lanes that control the pace of star birth. Their dust acts like a pressure valve, resisting collapse until enough material accumulates to overwhelm magnetic fields and turbulence. This delicate balance explains why Cygnus X doesn't detonate all its stellar fuel at once. Instead, it parcels out star formation in epochs, with dark nebulae serving as both warehouses and gatekeepers for the galaxy's raw materials. Infrared eyes reveal another secret: these aren't static structures. The dark lanes writhe and reconfigure over centuries, their movements etched by the very stars they birth. Young, massive stars emit fierce winds that carve bubbles and tunnels through the dust, while supernovae from previous generations send shockwaves rippling through the complex, compressing new pockets of gas into future nurseries. It's a self-perpetuating cycle. Darkness gives rise to light, and light reshapes darkness in a dance that's been ongoing for millions of years. Cygnus X challenges our notion of dark nebulae as passive entities. Here, they're dynamic architects, shaping not just individual stars but the entire ecosystem of a galactic neighborhood. Every shadow hides motion, every void hums with potential, and in their depths, the next generation of stellar titans waits for gravity to sound their wake-up call. The Taurus molecular cloud drifts through our cosmic backyard close enough that its dark tendrils cast shadows we can study in astonishing detail. Located a mere 450 light-years away, this sprawling complex of dust and gas is one of the nearest stellar nurseries to Earth, offering astronomers a front-row seat to the messy, magnificent process of star birth. Unlike the dramatic silhouettes of the Horsehead or the Pipe, Taurus's dark nebulae, like Barnard 215, appear as wispy filaments, their edges frayed by subtle interactions with interstellar winds. But don't let their delicate appearance fool you. These shadows are cosmic cradles, their depths pulsing with the earliest whispers of new suns. What makes Taurus extraordinary isn't just its proximity, it's the sheer diversity of its star-forming activity. While massive complexes like Cygnus X birth stellar giants, Taurus specializes in creating stars like our Sun, modest, stable, and perfect for nurturing planetary systems. Infrared telescopes have spotted over 400 young stellar objects here, each at a different stage of development. Some are still hidden within thick cocoons of dust, barely more than warm knots of gas. Others have begun to flicker to life, their nascent light scattering through the nebula's thinning veins. And a few have already cleared their surroundings, their stellar winds carving cavities in the dark cloud like bubbles rising through ink. Barnard 215, a serpentine dark lane winding through the complex, serves as a perfect example of Taurus's dynamism. At first glance, it's just another shadow, but radio observations reveal its secret. This filament thrums with internal motion, gas streams flowing along its length like water through a canyon. These flows aren't random, they're directed by the nebula's magnetic fields, which act like cosmic conveyor belts funneling material toward denser clumps. In some spots, the gas piles up into cores so dense they've begun to glow faintly in submillimeter wavelengths, the telltale sign of protostars taking shape. The real magic lies in the details. Because Taurus is so close, telescopes can resolve structures smaller than our solar system within its dark clouds. Ultra high-resolution images show intricate disk-like formations around infant stars, some already displaying gaps and spirals, potential signatures of planets coalescing from the dust. Other observations capture bizarre chemical gradients, where molecules like formaldehyde and methanol concentrate in specific zones, painting a picture of how organic chemistry evolves alongside young stars. It's like watching a cosmic recipe unfold in real time, with dark nebulae as the mixing bowls. Yet Taurus holds deeper mysteries. Unlike most star-forming regions, its dark clouds produce stars at a leisurely pace, with no massive stellar disruptors to stir up the gas. This quiet environment makes it an ideal laboratory for studying how stars form in isolation, free from the chaos of crowded clusters. The cloud's chemistry is equally puzzling. Certain molecules appear overabundant here, including complex organics normally associated with comet nuclei. Some scientists speculate that Taurus's dark lanes could be seeding future planetary systems with the building blocks of life, their icy grains preserving primordial chemistry untouched since the galaxy's early days. By combining observations from radio telescopes, infrared arrays, and even optical instruments peering through the nebula's thinner edges, astronomers are piecing together Taurus's life story, one that challenges assumptions about how darkness gives way to light. These clouds aren't just obscuring the cosmos, they're curating it, slowly transforming chaos into order, gas into stars, and dust into worlds. And because they're so tantalizingly close, every new revelation brings us nearer to answering the ultimate question: how did a cloud like this set the stage for our own existence? At the base of the Cone Nebula, where its shadowy pillar meets the glowing sea of gas around it, an interstellar battleground unfolds, one where gravity and radiation wage a silent war over the fate of future solar systems. This iconic dark nebula in Monoceros isn't just a static sculpture. It's a dynamic fortress, its dense core standing defiant against the hurricane-like winds blasting from newborn stars nearby. The secret to its resilience lies in its structure. Unlike the wispy tendrils of the Snake Nebula or the fractured patches of the northern Coalsack, the cone's base is a masterclass in cosmic architecture. Its dust and gas packed so tightly they form a natural shield against erosion. Peer closely at Hubble's images of this region, and you'll notice something extraordinary. The pillar's surface isn't smooth. It's pocked with tiny bumps and ridges like the weathered face of a cliff. These aren't random imperfections, they're evidence of the nebula's hidden scaffolding. Submillimeter telescopes reveal that the cone's interior is laced with intricate networks of magnetic fields, acting like rebar in concrete to reinforce the pillar against external forces. Meanwhile, the dust grains here are unusually sticky, coated in layers of frozen molecules that help them clump together into near indestructible aggregates. It's this combination of magnetism and chemistry that allows the nebula to endure stellar winds capable of stripping gas away at 500,000 miles per hour. But the real magic happens deeper inside. While the outer layers take the brunt of the radiation assault, the pillar's heart remains eerily calm, a quiet oasis where gravity can work undisturbed. Infrared observations show dozens of compact knots embedded within the base, each one a potential protostar drawing material inward. Some of these knots already glow faintly with the heat of collapse, their cores warming as they prepare to ignite. This layered defense destruction on the outside, creation within, makes the Cone Nebula a perfect natural laboratory for studying how star systems survive their violent births. What's most striking, though, is the nebula's resemblance to structures seen in far younger galaxies. The same processes shielding the cone's base may have protected the first star-forming regions in the early universe, where radiation from primeval stellar giants was even more intense. By decoding how this pillar persists, astronomers catch glimpses of how the cosmos itself learned to build sanctuaries for new worlds amid the chaos. The cone doesn't just hide stars, it holds blueprints for their survival. The Lupus dark clouds drift across the southern sky like tattered remnants of a cosmic curtain, their jagged edges fraying into the star-studded canvas of the constellation Lupus. Unlike the dramatic silhouettes of the Horsehead or the Pipe, these nebulae appear almost unfinished amorphous blobs of darkness with no clear symmetry, as if the universe absent-mindedly spilled its darkest ink across this corner of the galaxy. But within their chaotic forms lies a treasure trove for astronomers, a front-row seat to the birth of some of the universe's most mysterious objects, the failed stars known as brown dwarfs. What makes the Lupus clouds so special is their peculiar stellar output. While most star-forming regions produce a mix of sun-like stars and occasional giants, Lupus specializes in the small and strange. Infrared surveys reveal dozens of faint, warm objects embedded within the nebula's folds, not quite stars, not quite planets, but something in between. These brown dwarfs glow dimly with the heat of their slow gravitational collapse, never reaching the critical mass needed to ignite full hydrogen fusion. In most nebulae, they'd be overshadowed by brighter stellar siblings. Here, they're the main attraction. The Lupus complex offers a perfect storm of conditions for brown dwarf production. Its clouds are colder than typical star-forming regions, with just enough turbulence to fragment the gas into small, isolated clumps. Magnetic fields play a crucial role too, acting like cosmic brakes that prevent these clumps from gathering too much material. Combine that with the nebula's relatively low density, and you have a recipe for creating objects too hefty to be planets, yet too puny to shine like true stars. But the real revelation came when astronomers noticed something odd about the brown dwarfs here. Many of them float freely, unbound to any star, yet they bear the same chemical signatures as objects still forming within the dark clouds. This suggests they weren't ejected from planetary systems but formed solo, like starlight that never quite flickered to life. Some even harbor swirling disks of dust potential nurseries for planets orbiting failed suns. The Lupus clouds challenge our definitions of what a star truly is. Their irregular shapes, once dismissed as cosmic afterthoughts, turn out to be the perfect crucibles for nature's experiments at the boundary between star and planet. Every jagged filament, every wispy tendril holds clues to how the universe fills the gaps in its own taxonomy, not with bright beacons, but with dim, enigmatic objects hiding in plain sight. The dark river in Scorpius slithers across the sky like a serpent made of shadow, its sinuous curves linking the fiery glow of Antares to the star-studded fields near Rho Ophiuchi. This isn't just a chance alignment of dust, it's a cosmic highway, sculpted by forces both violent and subtle, where every twist tells a story of interstellar upheaval. Stretching over 10 degrees of the southern sky, the river's meandering path is so pronounced that ancient skywatchers marked it as a distinct celestial feature long before telescopes revealed its true nature. What they couldn't have known is that this dark ribbon is actually a fossil record of chaos, its shape molded by shock waves from stellar explosions that rocked this region millions of years ago. Radio telescopes peering into the river's depths have uncovered something extraordinary. Its dust lanes aren't just passively drifting, they ripple. Like the wake behind a speeding boat, these undulations are the lingering echoes of supernova blasts that tore through the area, compressing gas and dust into dense, twisted strands. Some sections of the river even show evidence of bulk flows, where entire segments of the nebula are moving en masse, dragged by the gravitational pull of hidden mass concentrations. This suggests the river isn't just a relic of past violence. It's still being shaped today, its course rewritten by the invisible tug of dark matter, or perhaps rogue stellar remnants lurking unseen. What makes the dark river truly unique is how it bridges two of the sky's most photogenic regions. At one end, Antares, a red supergiant so colossal it could swallow our solar system out to Jupiter, bathes the nebula's nearby tendrils in a faint crimson glow. At the other end, near Rho Ophiuchi, the river dissolves into a tapestry of blue reflection nebulae and golden stardust, creating one of the most breathtaking visual contrasts in the night sky. This transition isn't just scenic, it's astrophysically significant. The river acts as a cosmic filter, its dust selectively absorbing shorter blue wavelengths from background starlight while letting longer red tones pass through, effectively warming the color palette of everything lying beyond it. Yet the river's most tantalizing secret lies in what it carries. Submillimeter telescopes have detected complex organic molecules swirling within its currents, compounds like methanol and glycolaldehyde, the chemical precursors to life. These molecules thrive in the river's unique environment, where starlight from Antares is just strong enough to trigger chemical reactions, but not so intense as to tear the delicate compounds apart. Some scientists speculate that this dark corridor could be funneling these probiotic ingredients toward younger star systems downstream, seeding planets with the raw materials for biology before they've even fully formed. As astronomers continue to map the river's sinuous path, they're discovering it's far from solitary. Its currents interact with at least 3 other dark nebulae in the region, their material mingling at the boundaries like tributaries feeding a cosmic Amazon. These junctions create zones of intense compression, where gas reaches critical density thresholds and collapses into protostar stellar infants whose faint infrared glow is only now being revealed by cutting-edge observatories. The river, it seems, isn't just a relic or a pathway. It's a midwife helping to usher new suns into existence even as it preserves the echoes of ancient cataclysms in its winding course. The Elephant's Trunk Nebula coils through IC 1396 like a cosmic serpent frozen mid-strike, an intricate sculpture of dust and gas shaped by forces more violent than any earthly storm. This 3-light-year-long pillar doesn't just stand passively, it battles. On one side, the blistering radiation from HD 206267, a massive young star, hammers the structure with enough ultraviolet fury to ionize entire planets. On the other, the cold grip of gravity pulls inward, compressing the nebula's innermost pockets into tight knots where new stars flicker to life. The result: one of the most photogenic cosmic wrestling matches in the galaxy, where destruction and creation collide in real time. What makes the Elephant's Trunk so mesmerizing isn't just its silhouette, it's the physics behind its wrinkles. The nebula's surface ripples with dense globules, each one a tiny fortress against the stellar onslaught. These evaporating gaseous globules, or egg, are cosmic survivalists. Their outer layers erode like sandcastles in a hurricane, but their cores remain shielded long enough for gravity to work its magic. Inside, gas condenses into protostars, their faint infrared glow detectable only when viewed through telescopes like Spitzer or Webb. It's a paradoxical process. The same radiation that's tearing the nebula apart is also triggering the birth of its stellar successors. Zoom in closer, and the trunk reveals even stranger architecture. ULMA radio eyes have detected tendrils of carbon monoxide weaving through the pillar like reinforcement bars, their molecules locked in a frenetic dance. Some stream away from the nebula entirely, fleeing the radiation as ionized gas. Others spiral inward, drawn by the pull of forming stars. This intricate balance between escape and accretion determines the nebula's lifespan. Too much erosion, and the entire structure dissolves. Just enough compression, and new stars emerge from the wreckage. The most astonishing detail, though, hides in the shadows. At the trunk's base, nestled within its darkest folds, lies a cluster of newborn stars so young they're still swaddled in dusty cocoons. These aren't the blazing giants that carved the nebula, their modest suns, some no larger than Jupiter, their faint warmth only detectable at submillimeter wavelengths. Their presence hints at a hidden hierarchy within the chaos. While the brightest stars dominate the landscape, it's the smallest, darkest corners where the next generation quietly takes root. IC1396's masterpiece isn't just a static exhibit, it's a living lesson in stellar ecology. Every groove in the elephant's trunk, every evaporating globule, tells a story of how light shapes darkness and how darkness in turn nurtures new light. As telescopes track its slow-motion transformation, we're witnessing the universe's endless cycle of reinvention, written in dust and sculpted by starlight. Rising from the star-studded plains near Scorpius's tail, the Dark Tower stands like a monolith, a jagged spine of cosmic dust stretching over 30 light-years into the void. This isn't just another shadow against the Milky Way, it's a skyscraper of star-forming potential, its silhouette so stark it looks like a hole punched straight through the galaxy. Backlit by countless distant suns, the tower's edges glow with an eerie luminescence, every ridge and valley of its structure highlighted as if traced by celestial spotlights. But the real magic lies in what we can't see with visible light alone. Peering through the infrared eyes of telescopes like Spitzer and Herschel, astronomers have uncovered the tower's three-dimensional truth. What appears as a flat shadow in optical images is actually a labyrinth of nested filaments, their tendrils twisting through space like the roots of an ancient tree. Gravity has sculpted these dust lanes into dense knots, some with masses exceeding 200 suns, stellar embryos waiting for the spark of ignition. The entire structure hums with slow motion, gas streaming along magnetic field lines toward these pockets of future starlight. What makes the Dark Tower extraordinary isn't just its scale, it's the diversity of its stellar assembly line. Near the base, where the dust is thickest, protostars burrow deep within their dusty cocoons, detectable only by the faint heat signatures they emit. Higher up, where radiation from nearby stars has eroded the nebula's outer layers, adolescent stars flicker to life, their stellar winds carving bubbles into the surrounding darkness. This vertical gradient offers a snapshot of stellar evolution in progress, from birth to adolescence, all within a single towering structure. Radio telescopes have revealed something even more astonishing: the tower isn't standing still. It's swaying. Subtle Doppler shifts in molecular gas suggest the entire pillar oscillates, likely rocked by shock waves from past supernova or the gravitational tug of hidden objects. These vibrations aren't just cosmic noise, they're catalysts. Every tremor sends ripples through the gas, compressing it in some regions and stretching it in others, accelerating the collapse of future star systems. Yet the most tantalizing discovery lies at the tower's shadowy heart. ULMA high-resolution imaging has spotted a cluster of failed stars, brown dwarfs too small to ignite hydrogen fusion nestled among more typical stellar newborns. Their presence hints that this nebula operates on multiple scales, crafting everything from dim celestial embers to potential stellar giants. It's a reminder that darkness doesn't discriminate. Within its depths, the universe experiments with every possible outcome of cosmic chemistry. Standing sentinel near the galactic plane, the Dark Tower embodies the duality of all great dark nebulae. It's both a barrier to light and a bridge to creation. Every shadow along its length whispers the same truth. What hides from our eyes often holds the keys to understanding how the cosmos builds its brightest wonders. The Gulf of Mexico Nebula sprawls across Sagittarius like a celestial ink blot, a vast, irregular shadow that seems to swallow the Milky Way starlight whole. Named for its uncanny resemblance to the earthly body of water, this dark nebula isn't just a hole in the sky. It's a dynamic frontier where dust and gas churn in slow motion, concealing some of the galaxy's youngest stellar inhabitants. What makes this cosmic gulf so compelling isn't just its shape. It's the way it interacts with its luminous neighbor, the Lagoon Nebula, creating a striking contrast between light and dark that tells a deeper story of stellar birth and cosmic erosion. At first glance, the gulf appears as a void, a stark absence in the glittering backdrop of the galaxy's core. But infrared telescopes reveal its true nature, a dense, turbulent cloud of molecular gas, threaded with filaments so cold they hover just a few degrees above absolute zero. These shadowy tendrils aren't static. They're actively collapsing under their own gravity, forming compact cores where new stars ignite in silence, their light smothered by the very dust that birthed them. Unlike the lagoon's blazing stellar factories next door, the Gulf's nurseries operate in stealth, their newborn suns detectable only by the faint heat signatures they emit at submillimeter wavelengths. The relationship between these two nebulae is a cosmic dance of opposites. The lagoon blazes with the energy of massive young stars, their ultraviolet radiation sculpting nearby gas into glowing ridges and caverns. Meanwhile, the Gulf acts as a protective barrier, its dark bulk shielding pockets of star formation from that same destructive energy. In some places, the boundary between them isn't just a transition, it's a battlefield. Shockwaves from the lagoon's stellar winds crash into the Gulf's densest regions, compressing the gas into new generations of stars even as they erode the nebula's outer layers. It's a paradox, destruction fueling creation at the edge of darkness. What truly sets the Gulf apart, though, is its role as a time capsule. While the lagoon's stars announce their presence with brilliant light, the Gulf's stellar infants remain hidden, their development slowed by the very conditions that nurture them. Some of these protostars are so young they haven't yet begun fusing hydrogen. They're little more than warm knots of gas, wrapped in cocoons of icy dust. Studying them offers a rare glimpse into the earliest stages of stellar evolution, a window into processes usually obscured by their own luminous aftermath. Yet the Gulf's most tantalizing secret might lie in its shadows. Radio observations have detected bizarre, ring-like structures within its depths, features that resemble shock fronts from ancient supernova or perhaps the echoes of long-dead stars. These ghostly imprints suggest the Gulf wasn't always the quiet backwater it appears today. It may have once been a site of violent stellar deaths, its dust enriched by the heavy elements those explosions scattered. Now, that same material is being recycled into new stars, blending the past and future in a single, shadowy expanse. As telescopes peer deeper into this cosmic gulf, they're uncovering a reality far richer than its name implies. This isn't just a dark patch, it's a living laboratory where the universe's most fundamental processes unfold behind a veil of dust, waiting for the right tools and the right questions to reveal their secrets. From beneath the Seagull Nebula's outstretched wings, dark tendrils creep like skeletal fingers, shadowy partitions carving this cosmic bird into distinct realms of light and chaos. While the nebula's glowing hydrogen clouds dominate telescopic portraits, it's the Inkai lanes snaking through them that hold the real power. These aren't mere voids, they're dense molecular walls, shepherding ionized gas into towering pillars and cavernous bubbles, shaping the nebula's evolution one stellar wind at a time. At the heart of this dynamic lies the Seagull's beak, a region dubbed Sharpless 296. Here, dark filaments intersect like frayed rope, dividing the nebula's ionized zones into discrete cells. Each partition acts as a pressure valve, containing the furious energy of newborn stars while allowing slow leaks of radiation to sculpt adjacent gas. The result is a mosaic of microenvironments, some blistering with ultraviolet fury, others eerily calm, their chemistry preserved in deep freeze. Radio observations reveal these dark borders are in constant motion, expanding and contracting as stellar winds buffet them from within. Infrared telescopes expose an even more intricate dance. The nebula's shadowy veins aren't uniform. Some are riddled with porous gaps where radiation seeps through, creating glowing stalactites of ionized gas that drip toward the void. Others form near impenetrable barricades, behind which protostars cluster like eggs in a nest, shielded from the very radiation that birthed them. This interplay between containment and erosion gives the seagull its unmistakable plumage, feathery wisps of glowing gas on one side, razor-sharp shadows on the other. What makes these dark lanes truly remarkable is their role as cosmic archivists. Spectroscopic analysis shows their dust grains are coated in complex ices, frozen relics of chemical reactions that occurred when the nebula was just a cold, dark cloud. As new stars ignite, their radiation peels away these icy layers like pages in a book, revealing a timeline of the nebula's transformation from inert dust to stellar nursery. Some filaments even display bizarre frost lines, where temperature gradients have sorted molecules into distinct bands. Water ice here, carbon monoxide there, like rings in a tree trunk marking eras of growth. Yet the seagull's shadows aren't just passive observers. Their gravity subtly steers the nebula's expansion, funneling supernova shockwaves into channels that trigger fresh rounds of star formation at their edges. In one striking case, a dark spur has redirected stellar winds for millennia, sculpting a tunnel through the nebula that now glows like a neon-lit avian windpipe. This constant negotiation between darkness and light, between structure and chaos, ensures the seagull will keep evolving, its silhouette shifting over eons as old stars fade and new ones emerge from the Inkai depths that birthed them. The dark mark in Aura lurks near the Milky Way's bustling plain, an unassuming smudge of cosmic dust with a hidden secret. This shadowy patch is laced with metal. Not the solid kind you'd find on Earth, but atoms heavier than hydrogen and helium, forged in the hearts of long-dead stars and scattered across the galaxy by supernova. While most dark nebulae are pristine clouds of primordial gas, the dark mark's dust grains glitter with unexpected contaminants: iron, silicon, even traces of gold, a celestial junkyard where the remnants of stellar explosions have gathered and mixed with the cold void. What makes this nebula so puzzling isn't just the presence of these metals, it's their concentration. Spectroscopy reveals up to 50% more heavy elements here than in similar dark clouds nearby, as if this particular patch of space hoarded the aftermath of ancient cataclysms. One theory suggests the dark mark might lie along the trajectory of a past supernova shockwave, its dust acting like a cosmic sponge, soaking up the ejected material as the blast front rolled through. Radio telescopes have even detected odd, filamentary structures within the nebula wrinkles in space that could be the fossilized imprint of that violent encounter, frozen in time. But there's another twist. These metals aren't just sitting idle. They're changing how the nebula behaves. Normally, interstellar dust is a passive player, drifting aimlessly until gravity pulls it into star-forming clumps. But metal-rich grains like those in the dark mark are more efficient at radiating away heat, allowing the gas to cool faster and collapse more readily. Computer simulations show this could accelerate star formation, turning what should be a sluggish process into something far more dynamic. Infrared observations support this idea. Deep within the nebula's darkest folds, astronomers have spotted dense cores glowing with the faint warmth of impending stellar birth, seeds of future suns enriched with a chemical legacy older than our solar system. Some of these cores show unusual spectral signatures, hinting at exotic ices forming on their surfaces, where metals might act as catalysts for complex chemistry. It's a reminder that darkness isn't inert. It's a crucible where the ashes of dead stars stir new life into being. Yet the dark mark's greatest mystery might be its sheer isolation. Most metal-enriched nebulae cluster near active star-forming regions, their heavy elements recycled through generations of stellar births and deaths. This one sits oddly alone, a metallurgist's workshop in the galactic hinterlands. Could it have drifted here from somewhere else, carrying its precious cargo across light years? Or is it evidence of a forgotten stellar tragedy, a massive star that died unseen, its remains settling into this quiet corner of Aura? As telescopes probe deeper, the answers might rewrite our understanding of how galaxies distribute their building blocks, not in smooth gradients, but in patches and veins like precious ore threaded through stone. The dark mark doesn't just obscure light, it illuminates a truth about the cosmos. Even in the deepest shadows, the universe is always working, always transforming, turning the debris of the past into the raw materials of what's to come. The Cepheus Dark Nebula complex sprawls across the constellation like spilled ink diffusing through water, a mesmerizing labyrinth of shadowy tendrils, each one branching into ever smaller filaments in a pattern that seems almost mathematical. At its heart lies Barnard 150, a twisted ribbon of dust stretching over 10 light-years, its silhouette so intricate that astronomers initially struggled to explain how nature could sculpt something so perfectly imperfect. This isn't just a cosmic afterthought, it's a living puzzle, one that's rewriting our understanding of how chaos and order intertwine in the vacuum of space. What makes this complex so extraordinary isn't just its scale, it's the way its structure defies conventional astrophysics. Zoom in on any section of Barnard 150, and you'll notice something uncanny. The same branching patterns repeat at every level, from the grandest curves down to the tiniest detectable wisps. It's a fractal phenomenon, like a cosmic coastline where every new layer of magnification reveals fresh detail. Supercomputer simulations suggest this complexity emerges from interstellar turbulence, the same forces that stir cream into coffee, but operating across light years and powered by supernova shockwaves, stellar winds, and the Milky Way's own rotation. Yet the nebula's real-world structure is even more nuanced than models predict, hinting at gaps in our grasp of how energy cascades through the void. Radio telescopes have uncovered another layer of mystery. The nebula's filaments aren't static, they vibrate, resonating with subtle waves that propagate like plucked guitar strings. These oscillations aren't random, they follow patterns linked to the cloud's magnetic fields, which act like invisible scaffolding, guiding the dust into its intricate formations. Some sections of Barnard 150 even exhibit coherent flows, where gas moves in synchronized streams along the filaments, as if the entire structure were a cosmic pipeline funneling material toward hidden stellar nurseries. But the most startling revelation comes from looking sideways. While most dark nebulae appear as two-dimensional silhouettes, the Cepheus complex reveals its true depth when studied through radio and infrared eyes. Barnard 150 isn't a flat ribbon, it's a twisted rope, its strands braided by gravitational interactions with neighboring clouds. At certain nodes, these braids tighten into knots so dense they've begun glowing faintly in submillimeter wavelengths, the telltale signature of protostars in their earliest, darkest stages of formation. What emerges is a portrait of chaos with purpose. This nebula's fractal beauty isn't decorative, it's functional, a natural optimization for turning scattered gas into stars. Every twist and fork maximizes surface area, allowing radiation and turbulence to efficiently redistribute energy. Every vibrating filament acts as a cosmic conveyor belt, feeding material toward gravitational collapse points. Even the magnetic fields, once thought to merely constrain the chaos, now appear to actively participate in shaping it, like invisible hands molding clay. The Cepheus complex challenges us to rethink darkness not as an absence but as a dynamic medium, one where turbulence writes its own rules, where randomness births structure, and where the universe's most captivating patterns emerge from the very forces that ought to erase them. As telescopes peer deeper into its shadowy folds, they're uncovering a truth as old as time itself. Even in the void, there's a method to the madness. The chameleon dark nebula drifts silently through the southern skies, a wispy shadow so faint it was only catalogued after its more luminous neighbors stole the spotlight. While the constellation's glowing nebulae paint vibrant strokes across the canvas of space, This unassuming cloud prefers subtlety, its edges blending so seamlessly into the cosmic backdrop that it takes specialized telescopes to trace its full form. Yet within its delicate folds lies a cosmic tightrope act, a masterclass in equilibrium where opposing forces dance in perfect, precarious balance. Unlike the dense pillars of the Eagle Nebula or the dramatic contours of the Horsehead, Chameleon's dark cloud appears almost ethereal, a veil of dust so thinly spread that starlight barely dims as it passes through. This faintness isn't a sign of insignificance but of a remarkable stability. Most molecular clouds either collapse into stars or dissipate entirely within a few million years. This one has lingered for tens of millions, resisting both outcomes through a combination of low density and gentle turbulence. Imagine a souffle that never falls, gas particles buffeted just enough by microturbulence to counteract gravity's pull, yet not so violently that the cloud tears itself apart. Infrared observations reveal the secret to this longevity. The nebula's dust grains are extraordinarily fluffy, their fractal structures creating maximum surface area with minimal mass. This gives the cloud an unexpectedly strong defense against collapse, like a pile of feathers that resists compaction no matter how gently you press. Meanwhile, weak magnetic fields thread through the nebula like cosmic stitching, providing just enough support to keep gravity from gaining the upper hand. It's a system so finely tuned that even the gentle push of starlight from nearby hot stars plays a crucial role, its radiation pressure helping to maintain the nebula's delicate equilibrium. Yet Chameleon's stillness is deceptive. Deep within its coldest recesses, ALMA telescope data shows sparse pockets where the balance is finally tipping. A handful of dense cores have begun to glow faintly at submillimeter wavelengths, not the vibrant nurseries of more active star-forming regions, but slow, tentative contractions. These protostellar seeds may take 10 times longer to ignite than their counterparts in denser nebulae, offering astronomers an unprecedented opportunity to study star birth in ultra-slow motion. Some show bizarre chemical signatures, their ices enriched with organic molecules that normally get destroyed during faster collapse scenarios. What makes this nebula truly special is its role as a cosmic control sample. While astronomers often study star formation in extreme environments, dense clusters racked by supernova shocks or bathed in intense radiation, Chameleon presents the opposite scenario. Here, stars emerge from near isolation, their development governed by the most fundamental physics rather than chaotic external forces. It's like comparing a sprout growing in a quiet forest to one struggling through cracked pavement. Both tell us about life, but under vastly different conditions. The nebula's faint silhouette also serves as a reminder of how much we've overlooked. For every dramatic dark nebula that grabs our attention with sharp edges and high contrast, there may be dozens of these ghostly counterparts drifting unseen, their subtle influence on star formation going unaccounted in our models. As telescopes grow more sensitive, we're finding that the universe prefers shades of gray to absolute black. And in those subtle gradients, new chapters of cosmic history wait to be read. The dark nebula in Corona Australis crouches like a silent sentinel at the edge of its brighter neighbor, the blue-hued reflection nebula NGC 6729, a study in cosmic contrast. While most dark clouds dwell in crowded star-forming regions, this compact enigma floats in relative isolation, its dense core resisting the gravitational pull of nearby stellar nurseries. What makes this shadowy patch so compelling isn't just its solitude, it's the invisible hand shaping its destiny. Here, magnetic fields don't just influence star formation, they dominate it, turning this nebula into a natural laboratory for understanding how cosmic forces sculpt the birth of suns. Peering into the nebula's heart with radio telescopes reveals a strange order amid the chaos. Unlike the tangled filaments of the Cepheus complex or the swirling turbulence of Cygnus X, Corona Australis's dark cloud displays an eerie symmetry, its dust grains aligned like iron filings around a magnet, tracing field lines with near-perfect precision. This alignment isn't incidental. The nebula's magnetic field clocks in at over 5 times stronger than average for clouds of its size, powerful enough to counteract gravity's pull and press its gas into flattened sheets. Imagine trying to crumple a sheet of paper while magnets hold it taut. That's the tug of war playing out within this cosmic shadow. This magnetic stranglehold has startling consequences. While similar-sized dark nebulae elsewhere are bustling with protostars, Corona Australis's core remains eerily quiet. Submillimeter observations show dense knots of gas that should have collapsed into stars by now, except the field's grip keeps them suspended in stasis. Some pockets exhibit bizarre hourglass-shaped structures, their material funneled along magnetic channels like grains through an invisible hourglass. It's a stark reminder that star formation isn't just about mass and gravity. Sometimes the universe's invisible scaffolding calls the shots, yet the nebula's isolation adds another layer of intrigue. Most magnetically dominated clouds sit near Chinese letter 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 fields amplified by external shocks or compression. This one drifts apart, its strength intrinsic. One theory suggests it might be a relic fragment of an ancient larger cloud that was stripped away by passing stars, leaving behind only its most fortified core. Supporting this, astronomers have detected faint molecular streams trailing from the nebula, ghostly tendrils that could mark the path of its gradual erosion. The real fascination lies in the exceptions. Deep within the cloud's most shielded recesses, one tiny knot of gas has begun to glow faintly in infrared, a protostar defying the odds. Its very existence challenges models, proving that even the mightiest magnetic barriers can develop weak spots where gravity breaches the gates. Studying this renegade could reveal how the universe's most stubborn dark nebulae finally relinquish their treasures, not with a collapse but with a carefully negotiated surrender. As telescopes monitor this quiet cosmic standoff, they're uncovering a universal truth: darkness in space is never passive. Whether through gravity, turbulence, or magnetism, every shadow hums with invisible forces, each one writing its own rules for when and how light gets born. The dark nebula in Perseus isn't just another shadow against the Milky Way, it's a thread in the universe's grand tapestry, woven into the sprawling Perseus molecular cloud like a knot in cosmic yarn. Stretching over 500 light-years, this filament of dust and gas isn't drifting aimlessly. It's following invisible roadmaps, the galaxy's magnetic fields, which stretch and twist through space like the seams of an unseen fabric. What makes this nebula extraordinary isn't just its darkness, it's how perfectly it traces these hidden forces, offering astronomers a rare chance to map the scaffolding of the cosmos itself. Unlike the chaotic jumble of many dark nebulae, the Perseus filament displays an eerie regularity, its tendrils aligned along a single dominant axis. Radio telescopes reveal why the nebula's dust grains aren't scattered randomly. They're organized, their long axes pointing uniformly like compass needles responding to an immense magnetic field. This alignment isn't incidental. It's evidence of a slow, cosmic choreography where particles gradually rotate to match the galaxy's magnetic flow, a process taking millions of years. The result, a shadowy ribbon that acts like a giant arrow, pointing directly to the hidden forces shaping our corner of the universe. Zoom out, and the implications grow even more profound. This dark filament isn't isolated, it's part of a vast network threading through the Perseus molecular cloud, one segment in a web of similar structures spanning thousands of light-years. Together, they mirror the large-scale structure of the universe itself, where galaxies cluster along invisible filaments of dark matter. The difference. Here we can actually see the blueprint. As stars form along the nebula's densest knots, they illuminate the magnetic highways guiding their birth, like streetlights flickering to life along a dark freeway. But the real revelation comes from studying how this filament interacts with its surroundings. At certain points, the nebula's strands split and reconnect, forming Y-shaped junctions that resemble cosmic rivers merging. These aren't random either. Supercomputer simulations show they're the result of galactic turbulence, where shock waves from ancient supernova or spiral arm passages have folded and pressed the cloud over eons. Some junctions even glow faintly in submillimeter wavelengths, their gas compressed just enough to begin the slow collapse toward star formation. It's a snapshot of how chaos and order conspire to build the universe's structure, one magnetic thread at a time. Yet the most tantalizing detail lurks in the data. By measuring how starlight polarizes as it passes through the nebula, astronomers have detected subtle kinks in the magnetic field, places where the lines appear to twist or knuckle. These could be cosmic fingerprints of gravitational waves or passing dark matter clumps, their influence subtly warping the fabric of space. Alternatively, they might signal where the filament is under tension, strained by the competing pulls of neighboring clouds. Either way, each distortion tells a story, one written in the language of magnetism and dust. The Perseus Dark Nebula challenges us to rethink interstellar space as anything but empty. It's a dynamic arena where invisible forces sculpt matter into filaments, where darkness isn't the absence of light but the presence of structure waiting to be decoded. And as telescopes grow sharper, they're revealing an astonishing truth. What looks like a simple shadow could be the universe's way of sketching its blueprints in dust, showing us the hidden currents that guide everything from star birth to galaxy formation. The Lupus 3 Dark Nebula could easily be mistaken for a cosmic Rorschach test. One moment a void swallowing starlight, the next a luminous canvas painting the birth of suns. This striking nebula in the constellation Lupus embodies duality like no other. Its eastern half a thick curtain of dust, while its western edge gleams with the reflected glow of newborn stars. It's this dramatic contrast that makes Lupus 3 one of the most photographed dark nebulae, but beyond its beauty lies a deeper story, a snapshot of cosmic transition, where darkness and light aren't opposites but collaborators in stellar creation. What sets Lupus 3 apart is its rare transparency. Unlike the impenetrable blackness of Barnard 68, this nebula's dust is just thin enough to play tricks with light. In its darkest regions, background stars appear reddened and dimmed, their light filtered through countless icy grains. Along the edges, though, something magical happens. Young stars like HR 5996, barely 2 million years old, illuminate the surrounding dust like streetlights in fog, their blue-white glare scattering off microscopic particles to create an ethereal glow. This interplay turns the nebula into a natural spectrometer, revealing details about dust grain size and composition simply by how it bends and bounces starlight. The real fascination lies in how Lupus 3 documents stellar adolescence. Infrared telescopes peer through its veils to reveal dozens of protostars in varying stages of development. Some are still shrouded in thick cocoons, detectable only by their faint thermal whispers. Others have begun to emerge, their stellar winds carving teardrop-shaped cavities in the dust. A few, like the bright pair lighting up the nebula's western rim, have fully emerged, their radiation pressure pushing back the remnants of their dusty birthplace. This gradient offers a timeline of stellar evolution, all within one compact region, a cosmic classroom where every phase of star birth sits side by side. But Lupus 3's most valuable lesson is about destruction as a creative force. The very stars now illuminating its edges were born from the nebula's collapse, their formation triggered by shockwaves from passing spiral arms or nearby supernova. Now, as these young suns blaze to life, they're eroding the cloud that made them. their ultraviolet radiation evaporating nearby dust and halting further star formation in their immediate vicinity. It's a self-limiting process, one that ensures stellar nurseries don't overproduce, regulating the galaxy's star-forming rhythm. This delicate balance extends to the nebula's chemistry. Millimeter-wave telescopes have detected complex organic molecules like methanol and glycolaldehyde clinging to its dust grains compounds that would be destroyed by harsh starlight in more exposed regions. Here, they survive in the transitional zone where darkness gives way to light, shielded just enough to participate in the chemical reactions that might someday seed life on newly forming planets. Lupus 3 isn't just making stars, it's quietly assembling the ingredients for future biospheres. As we conclude our journey through these 25 cosmic shadows, Lupus 3 stands as a perfect finale, a reminder that darkness in space is never empty. Whether hiding stellar embryos, amplifying magnetic fields, or sculpting galactic architecture, dark nebulae are the universe's quiet architects. They challenge our perception of nothingness, proving that what looks like absence is often the most fertile ground for creation. And in their depths, the next chapters of cosmic history are already being written, one dust grain at a time. From the ink-black void of Barnard 68 to the delicate filaments of Lupus 3, these 25 dark nebulae have revealed a universe where shadows aren't empty, they're alive with possibility. Each one challenges what we thought we knew, whether it's the Snake Nebula's magnetic highways guiding star birth or the ink spot's unnaturally perfect darkness defying physics. Some, like the towering majesty of the Dark Tower, show us how gravity sculpts cosmic skyscrapers, while others, like the Chameleon Cloud, demonstrate how magnetism can freeze star formation in its tracks. Even the faintest patches, like the northern Coalsack, whisper secrets about the galaxy's history written in dust and scattered metals. What unites them all is the way they force astronomers to rethink the tools we use to explore the cosmos. When visible light fails, infrared and radio eyes pierce through, revealing protostars wrapped in dusty cocoons or tracing the invisible pull of magnetic fields. When traditional models can't explain why a nebula like the Dark Mark holds so much metal, new theories emerge about supernova shockwaves enriching the void. These shadows don't just hide stars, they expose the limits of our understanding, pushing telescopes and theories to evolve. Yet the greatest revelation isn't about any single nebula, it's the pattern they form together. From the frosted tendrils of Taurus to the fractal chaos of Cepheus, they prove darkness is a language. Some nebulae speak in the slow grammar of collapse, their gas crushing inward over eons. Others crackle with the rapid-fire syntax of turbulence, their shapes reshaped by stellar winds. And a few, like the Pipe Nebula, guard silent mysteries, their true depth only hinted at by the starlight they subtly redden and scatter. So now it's your turn. Which of these cosmic shadows pulled you deepest into wonder? Was it the Horsehead's battle against radiation or the ink spot's impossible flatness? The northern Coalsack's lonely journey or the great rift's illusion of a galactic divide? Let us know in the comments, and if you've enjoyed this journey through the universe's hidden corners, hit subscribe to keep exploring with us. The cosmos is vast, but every new discovery starts with a simple question: what's really hiding in the dark?